Hi, it's high-end test equipment porn teardown time again. This time we've got a Keithley DMM7510. Thank you very much, Keithley / Tektronix, because they're a Tektronix company, sent this in so we could take a squiz at it, and it's their high-end 7.5 digit multimeter. Hasn't been out all that long. It goes for around about $4,000, so it's really in the upper end of your extreme high end of your benchtop multimeters. But look at it, 7.5 digits. Look at the update rate. It is a million samples per second, 18-bit converter in there, 14 ppm accuracy. It's absolutely incredible. And yes, it's touchy-feely. And yes, it's got a knob. Look at that. Oh, I love a good knob. Now, clearly, this is what the new Keysight 34470A is designed to compete against. This Keithley one was released first, and then Agilent came to market with this one to try and compete. This is not going to be a review, but just basic, very quick overview. The Keysight one is much cheaper. It's around $2,900, so you're saving $1,100 difference. It's also 7.5 digit, but it's not as fast. It's only 5,000 or optional 50,000 samples per second. This does 1 million samples per second. The Keithley has an incredible resistance range. I'm talking like it's got a 1 ohm full scale range. Unbelievable. If you're into measuring low value resistances, whoa. But the Keysight has better current range. It's got a 1 microamp current range as opposed to a 10 microamp current range for the Keithley. But as you can see, even like on the 100 millivolt range here, absolutely no match. The Keysight is absolutely no match for the Keithley here. Look at the ridiculous update rate. I don't know. I haven't tried to use this thing yet. I don't know how many power line cycle filtering it's doing, something like that. But the fastest update we can get on the Keysight here, and we're a digit down. So it's only given us 4 decimal places on 100 millivolt range. This sucker's given us 5 decimal places. Oh, it's just, it's beautiful. And the buttons light up, and front and rear terminals, of course. So I can't get carried away here. Otherwise, I will turn this into like a mini review. But yes, it does. Also, it's all touchy-feely, much bigger screen than the Keysight, and it can do all sorts of data logging. It's got a big internal memory, all sorts of stuff. It can do it. A ridiculous amount of stuff, this meter. So yeah, just go read the user manual. Good luck with that. Wow, check it out. Those consistent spikes are very interesting. From minus 100 microvolts to minus 450 microvolts. Something to do with the sampling converter. I mean, we're not terminated on our input here. If I dick around there we go. Generating all sorts of crap. You can see that the 2 meters are about the same width and height, but the Keithley is an awful lot longer. Look at that. It's a really deep beast, and it's a bit in your face with this big plastic bit on the tilting bail here in red. Make it go faster. Keithley, a Tektronix company. And by the way, I just have to mention the fan on it. Really, really loud and rather annoying compared to the Keysight one. No contest. The Keysight is whisper quiet. This one is real, and not super loud, but bloody annoying when you got nothing else in your lab on. And that's the interesting part about this. Look at the back. Where's your traditional round fan hole? We don't get one. What is there, a little squirrel cage fan in there? It sounds like it's really going at a rate of knots. So yeah, I'm not sure what's going on there. We'll find out when we take it apart. But by far the best feature of this, look at these absolutely stunning HRC fuse holders. One for the 11 amp range and one for the lower 3.5 amp. Oh, that's just, why can't every bench multimeter have? Oh, they're really hard to screw back in. Sorry, I'm trying to get my hand out of the shot. But why can't every bench meter have massive HRC fuses like that? Fantastic. The Keysight, for example, all their meters, You've got to open the bloody things to change the fuses in them. But not such of a big deal on a bench multimeter. They typically don't get as abused as much on the current range generally, but geez, yeah, that's just really, really nice. Look at those. Oh, yeah, baby. Made in China. Oh, please? Really? And the rubber boot just slid off the back. There were no screws at all. I can only see a single screw on here, so I'm not sure if... Oh, that does it. One screw. One screw. Oh, and... Hello? After one screw, we are in like Flynn. Check it out. Wow, there's actually so much going on here. I don't know where to start, actually. Just all the little stuff that I'm seeing. But what I find the most fascinating is, look what they've got on the bottom here. They've got a complete, almost full-length PCB here just to connect, basically, a big ground shield. Plus, they're using that as a mounting point for the fan as well. So no, there's not a squirrel cage thing in there. It's just a regular, what is that, you know, a 60mm fan or whatever it is. But because the reason it's all whiny is because, well, there's not much airflow. It's not, you know, nicely ducted and everything else. So that's why it's probably got to try a lot harder to actually do that and run at a higher speed. So there you go. Anyway, I like the fact that they've taped down the wires there. That's quite nice. And how they've put a little cutout over here to put the wires in for the fan. That's all. It's just kind of novel. I wouldn't have expected to see a large shielded board on the bottom like that. And it's interesting to note the current jacks here. This is the 10 amp one. This is the 3 amp one. Has got a bit of special treatment. They've got this cutout here, and they've got that shield going directly to a big shield strap right around there. Why? Because the 3 amp range is the one that actually has the 10 microamps full scale. And of course, when you're talking 7.5 digits resolution on this thing, I think its resolution is 1 picoamp. So yeah, when you got 1 picoamp resolution, you want to take care of business with your shielding, and Keithley are one of the masters of shielding, so you can bet your bottom dollar they know what they're doing here. But yeah, nice little, look at that, little RF fingers there. One of the first things that really caught my eye, check out this groovy interconnect opto isolator board. You can tell it's an opto isolator because look at the big isolation slots cut right under there, and 3 packages like that. Dead giveaway that they're isolating the digital signals between this main board here, which will be the processor board, and all the analog stuff which is under this shielded can down on the bottom here. But they've used PCI, if I can I wiggle that out? I don't, it's kind of weird. Yeah, I don't think if I tried to get that out, I'd probably break it. I think you have to sort of, you know, like the way the thing's assembled and everything, the case, you might have to lift the lower one off first or vice versa. So if you try and get that out, but yeah, they've got this connector here, which is vertical, and then they got it going down here into another PCI connector down there on the analog board. And that's just brilliant. Someone was thinking from a system engineering point of view. And that wouldn't have been like a last minute addition either. Otherwise, all the opto isolator stuff would have gone on the main digital board here, or it could have gone on the analog board, whichever way you want to do it. So to put it smack in the middle like that, and then get that right angle, it's just, it's fantastic. Like why they didn't extend the board out, for example, and then like use a more traditional board-to-board interconnect between there. They could have even used like a 0.1 inch header or something like that going through, once again, a cutout in the shield there. But somebody's gone to a lot of trouble to gild the lily there. I like it. And we've got ourselves 2 main processors here and here, and a Spartan 6 FPGA. The processors are Freescale MPC 5125s. I'll link that in down below. They're 800 MIPS, 32-bit processors. Why they've got 2 of them, I'm not entirely sure. Maybe one to handle the sampling, although I thought maybe the Spartan 6 might be handling the sampling subsystem, something like that. Perhaps one would be handling the graphical user interface and all that sort of stuff. Anyway, these are designed as human-machine interface processors, and they drive a WXGA display and all that sort of jazz, which you've got in this thing in a typical upmarket, you know, high-end touchscreen, high-resolution user interface. But yeah, they got two separate processors there, exactly the same, so meh. So my first guess is the Spartan 6 FPGA here, it's going to be doing probably the sampling subsystem. That could be the sample memory tied onto there, perhaps. Not entirely sure, but it's definitely not like that we saw in the in other meters that we've seen that they can do the FPGA, the sampling FPGA functionality inside the FPGA. That's not what's going on here. Because it's on the digital board, it's not on the analog board as you'd expect it to be. So it's got to be doing, you know, it's got to be doing something after it's getting the data from the analog to digital converter. So yeah, that's probably handling all the automated sampling, because one of the big features of this meter is that it's a digitizer. It's a sample, 1 meg sample per second at, you know, 18 bits, and it's got a buttload of memory in it, and well, maybe that's what it's used for. Check out this part, it's just chock-a-block with DC to DC converters. You can tell by all the passives and the big ass inductors and caps in there. So dead giveaway, all that high density stuff, and look at all these ceramic caps all in parallel, things like that. So probably got to generate like 5 or 6 voltage rails. You know, all these processors need different cores. The Spartan 6 FPGA needs all different core voltages, and it's going off a ribbon cable going up here to the front panel. I believe that's what that'd be connecting up there. It's interesting to note that the front panel interface actually connects here, and you would think, okay, it's got to get through to one of these one of these applications processors down here, but they've stuck it right on the edge there and wedged all this DC to DC converter circuitry in the middle of it. So I'm not sure what the go is there. And that puppy in there is a TPS 65251 buck converter. So yeah, definitely going on there, but I don't know, maybe they're dropping these signals through to the lower layers and just getting them over. Yeah, it's just placed for convenience. Very interesting down here with this D-pack. They've obviously got room for a surface mount heatsink on there, but they decided not to fit it. For this transistor, it's not a voltage regulator, although it's could be being used as one, but yeah, it's a discrete transistor based on the Q designator. We've got ourselves one populated header and one unpopulated header. So this could be the JTAG programming header, for example, and well, either or this could be a serial interface port, for example, because a lot of these things will probably be running, you know, embedded Windows CE or something like that. Or I don't see a sticker on the back actually, so I'm not sure what OS this is running. If anyone knows, or if I find out, I'll annotate that in afterwards. But yeah, there could be a serial debug port or something like that. They're doing their grounding properly. Look at those shake-proof washers in there. 2 separate cables going out to different ground points. Well, they're serious about their 9-pin digital I/O port here. Look at all, looks like all individually fused and overall fused. Absolutely brilliant. Geez, belt and braces. And of course, given that we've got a second, looks like identical header over here, and we've got 2 of those processors, yeah, pretty much a dead giveaway that that's going to be the JTAG programming interface. Well, down on the analog board here from the side, hello Mr. TO92 2N3904, what are you doing there? We saw a TO92 package part on the Agilent unit for the voltage reference, so that it was outside. It was the thing that was controlling the heater element for the voltage reference, and it was outside, so it would get separate airflow. I wonder if they've done the same thing here, because there's a metal can right next to it, but it's a huge can. It goes all the way up there, so I don't think all of that is your voltage reference. But anyway, fascinating. And here's a big ass 4-terminal current shunt. I'll give you a better look at that. So it's like bugger wiring PCB traces to this thing. Let's just go, here's the main current here and here, the main wires coming in. Very nicely heat shrunk, by the way. Well done, bravo. And then one of the sense wires is coming off here. They've only got one sense wire because the other one is stitched all the way down there to ground, so they don't need the second sense wire. So it's relative to ground by the looks of it, but yeah, Now here's something I find quite strange. It looks normal on the top here. Here's one of the sense terminals, of course. So they've got that isolated from this ground trace around it. Okay, and they've got the sense wire going off. Okay, everything's hunky-dory, but that doesn't explain the big ground traces over there with all the via stitching. But look at the backside. Check this out. Look at this big solid trace going right across here between the high current side and the sense side. And all that via stitching in there as well. It almost defeats the entire purpose of having that nice 4-terminal current shunt in there. And there's your switch in, your main front rear terminal switch in there inside this metal shield can. You can see some isolation slots maybe down there between all the individual throws of that switch. And curiously, on this processor here, we've got a memory chip missing. There could be like another, maybe more on the bottom side. I don't know. We'll see. So I don't know. Is that an expanded memory option for the data login? Perhaps something like that. This processor over here has both chips fitted. And also, there is a reset switch not populated there. I wonder what that's for. Now, I'm really curious to know what's going on with this vertical board right near the front panel. And no, it's not near the input connectors. It's on the opposite side to the input connectors. We've got these shielded coaxes like this, which cross over like that, interestingly, with an isolated cutout. There's others on the other side there. And if we flip it over and take a look, in there, we'll have to get the board out to take a closer look, but those cables go into, you can see them stripped, the outer shield stripped off and then crimped, like terminated to the board there, and then looks like they go through some toroids there, and they've got some extra wires going through as well. Is that some sort of weird-ass current transformer or something? It's bizarre. I don't know what's going on there at all. We'll definitely have to get that board out. But anyway, nice little touch on the caps here. They've put some black gunk between the caps there just to stop them flapping around in the breeze. And on the main digital board, we've got ourselves some Nichicon brand caps there. Yeah, spared no expense. But unfortunately, I can't see what these caps here are on this front panel board or whatever it's called. We'll find out once we get a bit further. And if we take out this fan board here, ta-da! We're more in like Flynn. Check it out. Here is our analog board. Ah, beautiful. Now it's obvious what's going on with all the current shunt stuff we saw before. That little, looks like a Dale or something, current shunt resistor down the bottom down there. This is our 10 amp fuse holder here. This is our 10 amp jack on the back, this white one, this rear white one. So 10 amps into there, boom, over here through the orange wire, through the current shunt, boom, to ground, of course, because, well, that's what a multimeter in amps mode is. It's just a current shunt input to ground. Interestingly, though, the 3 amp one here, which we looked at before, and with the shield in, this is, oh man, this is just beautiful. All this looks like it's a machined sort of shield and part on there. Oh, it's just fantastic. Anyway, yeah, it looks like they've machined their own custom surround for that. So it's the same daggy fuse holder as this one with the daggy little, passivated nut on there, but they've gone to the effort to do like their own nylon washer plus their own screw-on metal shield over the back of that. Anyway, this is the 3 amp one. So this is the 3 amp input here, this white one, and it goes off unshielded, as all these wires are. Front and rear terminals are all unshielded, but that's the same in the Keysight one as well, so nothing wrong with that. Going through the heatsink into here, so this is all going to be our input switching that we saw before. You can probably see the rod going up there for the front rear panel switch. So that's all inside this. It looks plastic. So that's, yeah, so these are the front panel connections going over here and all into this switch-in box for the front rear panel connection. So it's going to have any input amps they might need for the low current ranges, things like that. And maybe the ADC is under there as well. That remains to be seen. Interestingly, we've got two little plastic. No, are they metal as well? I don't know. Anyway, we've got two cans. They must be either, if they are if they are plastic, then it'd be for stopping airflow over the voltage reference. Don't know where the voltage reference is yet. And there's our precision ceramic divider. Look at that. And then we get to see a lot of cutout stuff happening. This, like at first glance, I thought, aha, look at all the cutouts in there. Wow, trying to isolate those. But that must be the voltage reference on the other side. But no, that's just, look at the pinout. That's that PCI connector that goes over to the digital board we saw before. So yeah, they're just trying to isolate things there. They're doing that really, really well. And then if we get further down here, right next to, got some cutouts around what looks like maybe little 3-volt low dropout voltage regs. Perhaps we've got some cutouts around those. And yeah, Keithley knows what they're doing. As I said, they're the masters. You can see all the guard traces all around there as well for to equalize your and stop your leakage. We've got ourselves an Actel Pro ASIC 3 FPGA here. So is that running the ADC side of things? Are they doing that when they are using it? They say they're using an 18-bit digitizer, which sort of makes me think they're probably using a more off-the-shelf digitizer rather than, you know, rolling your own multi-slope integrator as we've seen on previous models. But I don't know that yet, haven't got far enough in there. But curiously, there's a second one, I presume, similar. It looks like the same footprint anyway, or, you know, same size and pitch package. So it might be the same Pro ASIC 3. Why that one is not populated, I'm not entirely sure. Maybe that's the sample expansion. I think this does have a sample expansion option, but why that'd be like some FPGA like that, doesn't seem to make sense. And what's this oscillator doing out here on its own, flapping in the breeze? I'm not sure. You know, it's obviously probably powering both. It'd be doing both. So even though it's a fair distance away from this one, they've only populated that. Interesting. And once again, we got ourselves another header over here, and that's a 10-pin header. Once again, it could be JTAG for the Actel Pro ASIC 3. Just wanted to show you the money shot on that fuse holder. Now I lifted this plastic cover off and we got some real interesting stuff under here. We hit the jackpot, folks. We've got more precision resistor networks and precision resistor up here. And another one flapping around in the breeze here, hand selected by wise old man with a grey beard, no doubt. We've got all the requisite stuff happening around our range switch here. That comes from the front panel. Nice little shaft going in there, very typical. And the wires are all, once again, all heat shrinked. They're pressed down to contacts on the PCB. Very nice. We've got some relay switching happening in there. But we've got some, well, there's one EPCOS GDT gas discharge tube down in there, aka spark gap. We've got another one over here. We've got some varistas here and here. They're monsters. They're absolutely the size of the package there. So, yeah, some really decent input protection happening around there. And that's about all she wrote, although I can see some, look at that, guard rings in there. You can see the exposed gold traces around the relays there. So, yeah, they're really taking care of business down in there for your real low current stuff. Of course, that's what you expect, because this thing has, I think, a minimum 10 microamp current range, but 7.5 digits resolution. So I think it's 1 picoamp, I think, or is it, yeah, 1 picoamp resolution on the thing. And check it out. Look, there's just these exposed gold guard traces everywhere, cutouts all over the place. It's like just all over the board here, all over the shop. Keithley are really going to town on their guard traces all the way over here. Check that out. Look at all that around there. Tons of it. Absolutely everywhere. This one's interesting actually. You can see the guard trace going around there from this. Look, is it from that SOT 23? I can't quite see here, but yeah, with this via and this trace here, they're obviously guarding. That's a critical trace. So they've got large separation there, and they're separated, and they're encasing that with a guard trace around there. So that is absolutely brilliant. And then the relay in there has little cutout slot, little routed slots in it for all that sort of stuff. So you can bet your bottom dollar that's a critical low current trace right there. And you can see more action happening around here. They've got that trace going all the way. Sorry, it's blocked by this huge resistor. I'll show you in a second. But yeah, this guard trace all the way around there. Then the slot cutouts underneath that chip. So these 4 pins on the end here, these are the ones that actually... Oh, no, I can get in there and... Oh, no, let me get in there and show you that up close. That's ridiculous. Check it out. I thought it was the 4 pads on that chip, but like the pins are, you know, 1 and 2 and, you know, what is it, 15 and 16 here. But no, look, that slot actually goes between pins 1 and 2 and 15 and 16 here. That's just crazy. So obviously and then the via just pops up here. Look at that, and it obviously goes over to that pin there, and then so pins 2 and 15 are the ones that they're trying to isolate on this particular switch. It's just it's a DG411 switch. Anyway, I got real excited when I saw this. I wanted to show it to you. Check out this hybrid resistor network here. Oh, usually you can't see anything, as we saw before with that one with the blue stuff. Usually it's all just covered and masked, but look at this. We can see all sorts of detail in that. It's just beautiful. Look who makes it. Fluke. But hey, that's not surprising because the evil Danaher group own Fluke, Tektronix, Keithley, and a whole bunch of others. Ugh, goodness. But anyway, that magic... That pawn comes from Fluke. Oh, some greybeard there. Oh, fantastic stuff. And they've got another smaller one down in there as well. You can see maybe some isolation slots cut between the individual pins. And yeah, these things are going to be ultra stable resistor network. Usually when you have a network like this, generally they're going to be trimmed to be, you know, precise values in the precise division ratio required by the analog to digital converter for the different ranges that gets switched in. I was so excited to find these top quality glass encapsulated precision resistor networks that I did a whole separate video on it before I finished this teardown. I raced in and did a separate video. It's about, I don't know, 17-20 minutes long, something like that. Check it out, talking about how these things are all laser trimmed. You can see the little laser trim marks in there, perhaps, even though I can't see them on the LCD here. And of course, almost certainly do some of that laser trimming through the glass, possibly after this thing is installed on the board. So yeah, that's real tricky business, and you know, these are top quality, basically as good as you'll find in any benchtop multimeter, and they're probably very likely technically superior technology to the ones used in the Keysight unit. And these are going to be one of the key reasons for the performance of this thing, which is, you know, nominal 16 ppm DC volts accuracy maximum over a year. So these, you know, the ratio of the resistors in these precision networks and the drift performance and everything else is going to be absolutely phenomenal to enable this. So this is why, likely why, one of the reasons this Keithley unit gets better performance than the Keysight 7.5 digit meter. But it costs more, $1,100 more. And my guess, given the low values of resistance inside this puppy, I think this array here is used as part of the current shunt resistors for the lower current ranges, because I can't find It's not obvious where there's any other current shunt resistors apart from the big 3 amp one that we can see. And this one here is your high voltage input divider resistor, 9.9 meg there and 100k. So yeah, a huge high voltage division ratio. There's basically only 2 resistors inside this thing. And my next guess is this more traditional ceramic resistor divider network, most likely not made by Fluke because it doesn't have the Fluke markings on the back. It's just got some other generic 8-digit number. That's probably for the resistance ranges, it'd be my guess. And this monster package that we've got here, look at it just freestanding there, 4-pin current shunt. You can see it's 0.1 ohms, so 100 milliohms, but it's only 1%, but as I said, doesn't matter. They trim that out, they calibrate that out in software. It is super ultra low drift, this puppy, so they're using that for one of the higher current ranges. And check it out, they've got another freestanding Vishay VFR resistor there as well, and that's individually, looks like individually hand selected and tweaked by someone with a grey beard, no doubt, or nude virgins, or both. And once again, it's very interesting to note all the TO92 packages here, and these are transistors, so why they're using TO92 packages, I don't know. Lots of individual cutouts between some of the pins on there. Very, very interesting, but as you can see, like, it's not trivial to design a high-end 7.5 digit, precision, industry-leading meter like this, to get your 16 ppm, a guaranteed spec, a 1-year spec, is just, there's a lot of magic, a lot of science that goes into designing and building and testing and calibrating and verifying a design like this. It's absolutely incredible. So if you think you can just, come along with your little off-the-shelf 18-bit converter that you can buy from DigiKey and a couple of precision resistors and a few op amps and she'll be right, yeah, you got a lot of things coming. That's hand-selected resistor there, R98. Look, do not bend. It's super duper special. So why is that one so critical? Sorry about the shaky camera work here, I'm just hand holding it. My guess would be that is the auto correction sample resistor. Now this is fascinating. Check out this puppy, completely isolated around there like that. And I had to go look up this number, SSM2212. I thought, what the hell is that? Look, you can see like there's differential, almost like differential pair coming in there, differential traces. Then they got some vias. They must, I presume, pop out on either the other side of the stem there, either this stem or this stem over here. But they've completely isolated that puppy so that there's no leakage into or out of that. I can't imagine that it's, well, after you find out what it is, I'll tell you, it's a dual matched transistor pair designed for, ultra low noise audio type applications. So they're using that as, as some sort of matched differential, some sort of matched transistor pair, maybe for a differential amp input or something like that. So anyway, they are completely matched. They want to either, so I think they're trying to keep the leakage out of there, of course, with the slots, as they're trying to do everywhere, but it's like normally you'd see that on like a voltage reference. So it's like the expansion, to stop expansion of the board. The FR4 PCB down here, the fiberglass material can expand, and then if you've got a real precision voltage reference in here, that can, minutely change that. So it's often common to see that sort of construction for a voltage reference. But in this case, it's not, or it could be part of the voltage reference perhaps, but it's not inside the any of the cans here, so where I expect the voltage reference to be. So yeah, some sort of, I don't know, anyway, some sort of matched differential pair. Very nice, gone to a lot of trouble there. And I think I know what these two cans here are doing. The silk screens are a dead giveaway. AD in, there we go, they've even got a test post there. Analog to the 18-bit digitizer, the analog to digital converter inside that can. And this one down here, bit of a giveaway. You might be able to see a little peeky through there. Oven driver. Aha! There's the oven driver circuit. So, bingo, your oven and your temperature and your voltage reference are going to be inside there. What's the bet that's an LTC 1000? Now this might look like and smell like an LTZ 1000, but check it out, it's not. Yes, it is still made by LT, that's the LT mark. It's the LT FLU1. And as you may have guessed from FLU, yes, it is a Fluke. It is a part specifically designed and manufactured custom for Fluke by Linear Technology. This is a really old part. It's been around for a long time. I've even heard that the NDA has expired on this thing because LT would not sell this to anyone else. It was Fluke basically were their only customer for this, and it was probably, you know, designed under contract by Fluke, hence why they wouldn't let them sell it to anyone else, because it's a key performance in Fluke's high-end multimeters, and they're still using the same one here, and it is a different topology to the LTZ 1000. So all the application circuit stuff you see around here, driving it, everything else is going to be different. About the only thing the same is that yes, it does have a built-in oven as well, and there's going to be, you know, feedback stuff there to stabilize the oven temperature. Now, whether or not its performance is as good as or better than the LTZ 1000, it depends on who you talk to. Can we get the real data on it, not just the datasheet data, but the real actual binned data? Because you can bet your bottom dollar these red and green marks here means something. Probably that it's been burned in, individually tested, characterized, hand selected, all that sort of jazz for their, their best performance 7.5 digit benchtop meter. And this is why a big part of the cost. It's interesting to note that, yeah, it's not socketed at all. It's directly onto the board. Of course, they can test the part before they solder it in. They can test and bin it, but it's different to the Keysight approach where we saw in the Keysight 7.5 digit meter. They put the whole thing on a separate module, on a separate board, once again with its own plastic carrier to keep all thermal effects and air circulation and thermal issues out of this thing. So by having the big plastic case around that, they're keeping all the airflow from the fan. And one of the most interesting things about this is the spiral arrangement of the cutout here. Now, look, as you can see, there's only 4 paths in and out. One there, one down there, one over there, and one up there. So, one trace through each one, both top and bottom, so you can probably have a maximum of like 8 traces coming in and out, but that's, probably enough for this thing, because it's just a voltage reference, so you need power in and basically reference voltage out. That's about it. They've got a complete cutout going all the way around here like that. So it's a spiral arrangement, and probably shouldn't do it, but I can, you probably can't see it there, but I can poke that board and make it move, because it's its own sort of, sprung arrangement in there by virtue of that spiral cutout. Now, the seismic man in me tells me, oh, what's the mechanical resonant frequency of this board when you mount it in there like that? And so it will have some sort of mechanical resonant frequency, and if I was designing this thing, I would put a reference accelerometer on this board and then sweep it through all the frequency ranges for the both operating and non-operating test conditions for various road transport. There's different standards for all these sorts of things. Anyway, I'd be doing that. I'm sure Keithley have done their homework on this, but yeah, this board will take out some of the vibration. So it's designed to mostly take out any thermal expansion issues, though. That's what it's really in there for. And look, it looks like they got a different footprint in there. I'm not sure if the FLU reference in there actually is available in different footprints or not. But anyway, that's really interesting. There's your voltage reference. Now, whether or not it's better performance than the LTZ 1000, depends who you talk to. And of course, as we noted before, the oven driver circuitry is outside of that plastic can, because that stuff to drive the oven takes a fair bit of current, so all that driver chip is going to heat up, so you don't want that inside your can that's designed for your voltage reference. So they sit it outside. They know what they're doing. All the shielding is all on the bottom. They've got a whole bottom plate made for this thing, and which is under there. I can't actually get that out. I have to take the whole board out. And then, of course, they've routed everything out of there just to really, just real belt and braces stuff to get rid of any thermal expansion issues whatsoever. And, of course, the plastic case went over the top of that. And yes, the cover for both the voltage reference and the analog to digital converter, which we think it is, we have to double check that in a minute, yes, is just plastic. It's not a shielding box at all. In this case, it's just designed to keep out the airflow. We've got shielding on the base of the board there. They don't necessarily need to shield this. They just need to keep out airflow from the fan that's cooling this thing, circulating air currents in there. Don't, waft over all of the parts and the voltage reference. But the voltage reference does have its own internal heater, but still, you don't want the ambient changing willy-nilly based on the fan. So, you want it to change really gradually, and that's what it's going to do by putting a cover on it. And here's what I think is possibly the ADC, although, because it's got that ADC in up here, that test point. So, these are DG switches, right? And we've got a DG switch over here. Look at all the slots, as we saw before, individually cut out between all the individual pins. Just brilliant. And all those gold guard traces. Oh, so sexy. Anyway, all we've got is that puppy there. Need a closer look. Well, I was wrong again. That's an LSK 389 from Linear Systems. Once again, link in the datasheet down below. An obscure beast, but it's like the other one we saw up here. It's a dual JFET amp. So there's no ADC under here at all. So all this stuff, they really don't want that to be thermally touched, hence why they're putting that cover over there. So there's no discrete off-the-shelf or even custom ASIC ADC in here. So clearly what they're doing is using these switches and FETs and these caps, as I'll talk about in a second, as a traditional multi-slope converter, which is what you get in these high-end multimeters. And I won't explain how multi-slope converters work. I've done a video on this, well, as part of a previous teardown, so I'll link that in down below so you can check it out. But clearly what they're using is these DG series switches. They're using these FETs to reset the sampling capacitors here and here. This C4 and C5 here. Clearly the sampling caps, very important. They're going to be real schmicko types, even though they look pretty ordinary. Look at the isolation slots under there. They definitely don't want those things to leak, because the whole idea of a multi-slope converter is to charge up, calculate how much time it takes to charge and discharge these integrating capacitors here and here. So they'd be using these FET switches, of course, real schmicko ones, to reset those caps. So that's clearly what they're doing, and almost certainly controlled via the Actel Pro ASIC 3 FPGA up there. That'd be doing all your multi-slope conversion at 1 meg samples per second. Thank you very much. Wow, check out that star grounding point. They got that one via there. And look, everything just branching off. Ah, beautiful. I love this. Depress switch S1 for NFP version. NFP stands for no front panel. You can actually buy this meter with no front panel on it. No touchy screen, nothing. Designed for, computer controlled applications, because this is primarily going to be used in, I don't know about a majority, but a huge percentage of applications are going to use this as a computer control thing. Hence the massive 1,000 page technical reference manual for it, most of which, like 600 or 700 pages, is just the command reference for all the commands and everything else for this thing. That's what it's designed for. Anyway, it looks like this switch is fitted for that no front panel version, so they just, they couldn't be bothered taking out the switch, and jumper linking things over. So it looks like that switch is installed for that version as well. It makes sense because, you assemble the same physical board on the production line that has the switch installed, and then that board can be used in either the front panel or non-front panel version. So it makes sense. And here's something interesting I just noticed. Look, the model number of this board, 2450-140EE0. Ta-da! Well, this explains a few things. This is the same board, same digital process logic board used in the 2450. Keithley's new SMU with it, like the same sort of, touchy-feely big screen graphical user interface running Linux or whatever it is. So they're reusing this board. That's quite smart. And if you take a look at the photo of the 2450 of the rear panel, it's exactly the same connector interface along here. So there's absolutely no doubt that they're reusing that board, and that explains quite a few things. It explains this sort of like a, unusual right angle opto isolated board to go over to the analog board. It explains why the fan wiring is all weird in here, is connected over here and goes all the way under there and over to the other side and all sorts of jazz like that. And that's what they're doing. They're shoehorning this same digital board into, well, now at least 2 products, and probably other products they've got in mind as well. Now check it out, this is quite interesting. Under this metal shield here, sorry I can't get the whole thing off, the whole unit has to come apart to allow me to get that out by the looks of it. But anyway, this is the true RMS converter I showed you before, the analog devices part that we're all familiar with. So this is the high voltage AC input side of things. You can tell it's high voltage because they've got the big isolation slots in there for the high voltage, big high voltage capacitor. I'll get a good angle on that in a minute. You can see, but I find this rather interesting. Look, here we go. R140 and 142 must be centered between their legs. These two ones, they must have an equal length leg either side. Why? I can't see any sort of, voltage isolation issue with that, really. But anyway, they're serious about how they want to form those legs and make sure there's an even leg each side. Fascinating. There you have it, a 0.22 microfarad 1000 volt peak high voltage cap tucked away in there. So that's directly coupling, like that's the AC. The AC input comes across here and directly AC couples through there and then is divided by that resistive divider we just saw and goes into our true RMS converter down in there. Oh, and by the way, I checked this port here, which I thought might have been like an RS-232 serial debug port for the Linux or whatever operating system they're using. And I checked the pinout and it doesn't seem to be the standard pinout. And the ground on this digital board, by the way, is not connected through to mains earth. So be very careful if you're going probing around here with your mains ground reference scope. Now if we follow the mains wiring from the rear IEC input connector here, it actually is bundled with all the rest of this. It's this grey cable you see here, and yes, it is actually a shielded cable, and it goes over to this interesting board which I mentioned before, which we now want to take a look at. But sorry, I'm not able to get the thing out, so we're a bit limited in what we can see, but it basically pops over to here onto the main board. Then we've got our mains power switch here. That's this green looking one there, and then it goes up, switched up to our regular switch mode, main switch mode power supply up here. And then this main switch mode power supply only looks like it has a single output, and that's this red and black wire, which, well, it's got 2 outputs, but I believe they're just wired in parallel. It goes over here to provide either like 5 volts or 12 volts or a single supply, heavy, quite high current supply for all the digital logic board. And the other one actually goes under here and it goes onto that, well, you probably can't see it, but there is a connector, and a 2-pin connector, red and black in there, applying power to some circuitry which is inside here. Really difficult to take a look at, but it's opto isolated by the looks of it from the mains input. So you might be able to see that opto isolator there. And if I spin this around, you can see the other chips in there. Now, one of them there has a little sticker on top, so that makes me think that that's some sort of little pre-programmed 8-bit micro or something, because it's quite common to put a sticker on the top with like a firmware revision or something like that after it's been programmed. So clearly, that circuitry in there is controlling something based on this, once again, 5 or 12 volt DC output from the switch mode power supply. Now we've got some other stuff which looks like it's on the mains side of things here. Little SOT 20, 5-pin SOT 23, a couple of 3-pins, and a couple of miscellaneous parts, maybe a resistor. It's not a capacitive divider to generate a small mains reference voltage, but yeah, I'm not sure what that's doing. Some sort of mains detection or something. Perhaps, not sure. Anyway, it is isolated because you can actually see through the PCB material itself and see that it's isolated from all the rest of this stuff over here, i.e. there's no copper on the bottom or top side of the board. So that's all connected and mains earth referenced. Right up there, you probably can't tell, but right up the back side of the board in there, they've also got a whole bunch of low voltage caps as well. So this is, as you'll see in a minute, a low voltage DC output, and you'll find out why. So this is this weird ass coax, sort of crisscrossed figure 8 coax thing I showed you before. And look, they've got the braids nicely soldered down to the board there, and crisscross faction, 4 of them are 2 crisscross on this side here and 2 crisscross on the other side of the board down in there, and these go through some toroids. Yes, looks like we've got some rectifier diodes and some bulk capacitance down there as well. Sorry about this angle, but it's probably the best I can do. You can see that on the other end of these are toroid rings, okay? There's 2 toroid rings side by side, and well, there's actually 2 on each side down in here, and then there's cable, those 2 coax cables running through there like that. So they loop back, hence why they're like a sort of figure 8 pattern going through those toroids. But look, we've got some really thick couple of turns here of enamel coated transformer wire, and this is exactly what it is. It's a transformer. You might notice down in there, right at the base of that enameled wire, it says plus 6 volts AC, and on the other side it says minus 6 volts AC, curiously. And we've got ourselves some diodes there and some filtering. So what we've got is a little transformer that's getting 6 volts AC out of it to power our analog board, and I'll show you that now. As I mentioned before, this switch mode power supply up here, that's, you know, the high power one, is only providing power to this digital board here, because hey, all that digital circuitry, all those heavy duty processors and everything running Linux or whatever, you know, it requires quite a bit of power. So, you know, it's like a couple of tens of watts power supply. And then it just goes over to this board. It doesn't go to the analog board. This switch mode power supply is not powering the analog board directly. It's powering it through this board here, which is like a switching power supply, so to speak, which seems to be some sort of switching power supply, so to speak, but really low noise one, because they want a low noise power supply for the analog board. It's crucial when you've got a state-of-the-art analog measurement instrument like this. So they're using this board and this sort of like handmade, hand-designed, handmade transformer. You can see the two toroid cores in there, and then they've got the other 2 on the other side feeding coaxes through like that in a figure 8 pattern, and then tapping off, also in that same core, tapping off some enamel transformer wire, turn it into a transformer, so to speak, a sort of like a low leakage, low noise transformer. Probably not very efficient, but it's doing that, and then they're rectifying the output so that it is super clean, which then goes over to the analog power supply. And here is where they power the analog power supply. It is this ribbon cable in here, this 10 or 12 way ribbon cable from here to here. This is supplying all the power from the board, and it comes from all these secondary side capacitors that are rectified from that 6 volt tap on that sort of like homemade transformer. Wow. And then you'll also notice there's another ribbon cable coming from the digital board here, and it goes all the way over and connects to the primary side of this transformer in here. So this is not power, this is not getting power out of here, powering the digital board, because the digital board's already powered with, or you know, the big high power thing here. It doesn't need it. So these are obviously some sort of control lines, and my guess is it's sending over the sampling clock so that this low noise transformer in here is synchronous with the sampling, whatever current sampling rate it's using. That's my best guess is what they're going on there, because when your noise is okay. If it's synchronous to your sampling, you can actually get rid of it. So I reckon that's what they're doing. This is a custom sort of Heath Robinson-ish kind of homemade transformer that is providing a super low noise output to power the analog rail. Wow, they've gone to an enormous amount of effort and complexity there to get a low noise supply. So here's the pins where that header comes up, and it goes into all this linear power supply stuff. No switching rubbish in here at all. You can see these thermal pads here underneath these, what are they, TSOP 8 packages or whatever. These are going to be little linear regulators, and if you check out, they'll be, you know, low noise ones. We've got plus minus 21 volts here. We've got 5 volts, we've got 3.3, we've got 2.5, we've got 1.5. So they will be powering, those lower rails there will be powering your Actel FPGA here. And plus minus 24 volts, not sure what they're using that for. They've also got plus minus 15 over here, because plus minus 24 is too high. That's, you know, 48 volts. That is 42 volts, plus minus 21 volts. 42 volts is too high for all your jelly bean op amps, you know, to work at. So they've also got a plus minus 15 volt rail tucked around in there as well. But they're all super duper low noise, tons of filter in here. And yeah, they've gone to a lot of effort to get clean power into the board, and then also some extra low noise local linear regulation as well. So I find that incredibly fascinating. They've gone to all that effort because, well, you know, they can't just have the switching power supply, just having the lower rails and then local regulation. No, it's, all the noise is going to get into the ground, so they're isolating the grounds between the two boards. They're doing everything. So this is a, you know, basically a noise isolation, ground isolation power supply transformer that powers all the analog stuff. It's brilliant. A lot of effort, and they've sort of like rolled their own. They haven't like just whacked in another transformer in there. No, sir, thank you very much. Got to roll our own with coaxes and our own enamel coated wire and everything else. That's the way to get low leakage. Yeah. So that's rather clever and effective way to get a low leakage transformer, because hey, you're using coaxes in there, heavily shielded coaxes on the primary side of the, that's the primary wind-in by the looks of it, and then the secondary wind-in is just your regular enamel-coated wire. And of course it still works because you've got, you know, magnetic coupling. You've got a magnetic core there in your ferrites there, your toroids there. So it still works as a transformer. It's just like an electrostatic shield. Probably similar to what you'll find in one of your typical mains isolation safety transformers. Not too dissimilar. So what that's going to do is really lower your capacitance between your primary and your secondary, i.e. the leakage and everything else, so that none of the switching crap from this main switch mode power supply, which they had to have because they haven't got room for a big ass linear transformer in here to power all the digital stuff. So they're using a switch mode, and they've gone, right, well, we've been forced to use a switch mode, but it's too noisy and we definitely don't want it to couple into our analog stuff. So we need a super duper low leakage thing with bugger all coupling. Let's roll our own. Fantastic. Thumbs up. And I'm curious to see what that metal shielding can and the shield on the braid on the coax in there is connected to. Is it connected to mains earth? Nope, not a sausage. And neither is the coax in there. You want to know where I reckon it's connected though? To our negative, which is our negative input. Our negative input here. Bingo. Look at that. It's connected to our input measurement ground. Ta-da! And of course that measurement ground is not mains ground earth referenced, okay? So they're doing that because that in an analog measurement system like this, the negative input reference becomes everything. So it is not tied to mains earth reference. So that becomes everything. That's why that they're using that as part of their shielded transformer in there to keep all the crap out from one side, from this switching supply over to the measurement subsystem. And I've powered it up and we've got some nice, what looks like multi-chip RGB LEDs in here doing the voltage monitoring, showing you if it's good. And they're all green at the moment, like this is 3.3 volt rail, another 3.3, 1.5, 1.4 is it? Well, sorry, 1.8, 1.4, and lots of other status. These are probably some sort of digital, the processor's running, blah, 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 blah. And even these ones over here for the power supply, good, they could actually be, there might be some analog comparators in there or something actually driving those to see if it's within threshold or not. So yeah, that's really good. They've gone to a lot of effort down there. We've got another blue one down here, not sure what that's doing, and there's a tiny little one down on this board down here, and it is lit. It is lit, I can assure you, but you probably might have a hard time seeing that, but it's barely on, but it's there. Maybe it's designed to come on real bright in some sort of fault condition perhaps. And there's one red LED down there, not a multicolored one, and that just indicates that the FPGA is running, and it tells you on the silk screen, FPGA running. Thank you very much. Yes, it is running, and bloody hell, this fan is annoying. It's like tacked on as an afterthought to the whole design. I really don't like it. It's whirring away. It's got a hopeless path in there for, it's right against the backside of the case. Look, it's hopeless. So they've just sort of run out of design decisions at the end. It's not well engineered, and that's the issue. That's the compromise you get when you reuse that digital board on the bottom that we saw, and you sort of shoehorn the product into there. You sort of have to design around that, whereas something like the Keysight one, much better design because it's specifically designed from the ground up to fit in that case, and it's smaller, it's more optimized. But this one, they've done, apart from the fan though, they've done a really good job at it, as I've shown before. But yeah, that's just afterthought almost, the fan and that shielding board. Down on the front panel board here, here's a Greyhill, good brand rotary encoder. That's our front panel knob. And then it looks like we've got another JTAG header down there. They've probably got another FPGA or processor to handle the LCD on the front. So yeah, sorry, that one looks like probably a real pain in the ass to get out. And for those wondering, I have no doubt that these connectors on the back are tellurium copper. They look really quite schmick. So yeah, they're low thermal EMF, of course, as you'd expect in an instrument of this class, 7.5 digits. And there's the banana plug holder on the front, and it's they've done it fairly well, but it's not as nice as the Keysight solution with their custom molded right angle thing they've got inside there. This one's still pretty good though. So there you have it. That's a look inside the new Keithley DMM7510, and generally it's incredibly impressive the amount of technology that goes into this thing. And well, yeah, you can see where your $4,000 goes in a lot of stuff in here. There's a lot more stuff in here than what we saw inside the Keysight. Lots of finer touches with the the better precision trimmed resistor networks, a secondary low noise power supply, and all sorts of stuff. They really have gone to town on this, so I have no doubt the thing is going to perform. It's very, very impressive indeed. So thank you very much, Keithley, for sending this one in to give us a look. Sorry I didn't want to take out all the board. It would really be a lot of work to get it all out and all the metal work out, and I'd have to disconnect everything, and it's just going to be a real mess. So yeah, there are parts on the underside of the boards here, but it doesn't look like much. So I expect those just to be, you know, ancillary, you know, bypass caps and the odd amp here and there, and, you know, other just miscellaneous stuff. I think we're seeing all the really interesting stuff on the top here. And as always, there are high-res teardown photos of what I could get anyway at EEVblog.com, so linked in down below. Check out the high-res teardown photos. Yes, they're available in the full resolution I take with my camera. If you're wondering what I take my shots with, it's an old Olympus E510 micro 4/3, 10 megapixel. It's nothing fancy. It's got a 35mm macro lens on it that works really quite well, and that's what I take my photos with. So yeah, a bit old school, geez, old school, you know, like it is reasonably old, but it does good macro shots. So that's where I got my macro shots for the resistor networks and things like that. So that works really well. If I had a more professional, like a proper light tent and stuff like that, I just do it in my ambient light here. So it's, you know, it's not that great. I need more light to get better photos and, you know, more even and stuff like that. But I do the best I can with the teardown photos. Anyway, if you want to discuss it, jump on over to the EEVblog forum. I'll leave YouTube or blog comments. And as always, if you liked it, please give it a big thumbs up. Catch you next time. Oh, by the way, if you're wondering why this video might be a bit patchy, it was shot over 3 days because I was doing various things, and I shot that resistor network video in between, and then I lost footage on my Canon HF G30 camera here. Grr! Pain in the ass. I did it to myself again. I shot a couple of hours shooting this footage this morning, finishing off. I thought I'd finished it, but no, lost all the footage because the SD card issues. Look, I've explained it before. Anyway, pain in the ass. It happens on my Sony camera too, by the way. It's part of the SD file format thing. Anyway, lost all the bloody footage, and I had to go reshoot it. So I probably missed some stuff, or if I was, you know, a bit short there with, you know, doing the final bit at the end. Sorry, it's just a pain in the ass. Anyway, this one took me a long time, which is why I'm not going to go in there and disconnect it, you know, take it all apart. I've just had enough tearing down of this thing. Catch you next time.